Let's discuss another very important class of resistive sensors called strain gauges. We'll start looking at strain gauges by just looking at a piece of wire. Okay, so here's a piece of wire. The resistivity of the wire is rho, the length is L, and the area is A. What is the resistance of this wire? I'm sure you know that it is just given by rho L over A. Okay, now what happens when you pull this wire? That's the question that you can ask. And as you pull this wire, um, um, the relationship between the stress and the strain. By the stress, we mean the force applied on the wire, and by the strain, we mean how much the wire extends is given by this kind of a curve, right? So when the stress is very small, you have a linear strain, or let's put it another way. For small strains, uh, to get small strains, you can the strain is proportional to the stress. Okay, so as you start pulling the wire, the wire starts to extend in proportion to the force that you apply on it. Now, uh, so initially there is a proportional relationship, and this region is usually called the elastic region of the metallic wire. This is basically valid for metals, this curve. So this is called the elastic region because in this region, if you apply a force, the wire extends, but if you leave the wire comes back to its normal shape. Okay, after some time, at some point what happens is, once it reaches its yield strength, the wire no longer returns back to its original shape. You have pulled it so much that now you have made a plastic deformation in the wire. And after the yield strength, the relationship between strain and stress no longer remains linear, but you have a curve like this till a point when you have now, which is called the ultimate strength. Beyond the ultimate strength, actually something called the necking happens. Necking is the phenomenon where actually, to pull the wire more, the wire is so damaged that to pull the wire more, you need less and less strength, right? So the more you pull, the lesser the strength you need to pull it a little bit more. And finally, the wire just fractures and breaks apart. So that's how this wire behaves as as you put strain on it. Now, why are we looking at this curve? We're looking at this curve because this is the principle in which strain gauges work. As the name suggests, strain gauges are sensors that measure strain. Okay, and of course, in most cases, strain comes because of an application of force on the strain gauge. And one of the simplest strain gauges is just a wire. Okay, and what we want is in a strain gauge the wire to work in this elastic region, right? Because you want the strain gauge, as the stress is applied on it, you want the strain gauge to stretch, and as soon as the force is released, you want the strain gauge to come back to its original shape. You don't want it to remain extended, so you don't want the strain gauge to go beyond the yield strength. Okay, so let's look at this deformation in the elastic region a little more carefully. Okay, so if this is a wire and you stretch it, so how does the resistance change? We can easily write dr over r as this equation here. So the change in resistance depends on the change in resistivity. So as the wire is stretched, maybe the resistivity itself, the properties of the metal itself change. You can also have dimensional effects. So as you stretch the wire, the length of the wire is increasing, and probably the area of the wire is decreasing, and both these cause some kind of change in resistance. I will leave you to derive this equation. It's a fairly straightforward thing, and I'm sure you would be able to do it. Okay, so but as you can imagine, there might be some relation between the change in length and the change in area, right? Because as you pull the wire becomes longer. You expect the wire to become thinner as well. Okay, so let's try to look at that relationship now. This The relationship of the diameter of a wire to its length as the wire is pulled is related by the what is called the Poisson's ratio. Okay, so if you look at this equation, as the length changes, or let's say as the length increases, the diameter of the wire is going to reduce, and the proportionality constant is called the Poisson's ratio, and it is usually between 0 and 0.5. Okay, so for metals it's usually below zero point 0.5. You would If you have a wire that maintains its volume as you pull it, the Poisson's ratio should be 0.5, and rubber is a close approximation. So as you pull rubber, the volume of the material remains the same, but in other cases the volume changes. Okay? So we can take this equation and we can now plug it back into the previous equation where we wrote the equation for the change in resistance. And if you do that, you get, we had this equation, and now what we do is, instead of this excuse me, instead of this change in area, we can actually write this in terms of the change of length by putting the Poisson's ratio in here. Okay, so then we get two effects. So strain gauge, the resistivity of a strain gauge, the resistance of a strain gauge changes because of two effects. One is the change of length, and this is the dimensional effect. This is because the dimensions of the strain gauge or the wire is changing, so the resistance changes. Another effect is because of the resistivity of the sensor. Okay, as you're pulling the wire, the resistivity of the sensor changes, and therefore the resistance changes. This is called the piezoresistive effect. Okay, and in usual strain gauges, what we would want is, if you are trying to record strains, right? What is strain? A strain is a change in length. Basically, dl over l would be the strain. So you want the resistance to change entirely because of this and not because of this resistive effect. Okay, so one way of characterizing strain gauges is by using gauge factor, and gauge factor is given by uh, basically the fractional change in resistance over the fractional change in strain, or the strain in the wire. The fractional change in length is called the strain, right? So the fractional change in resistance over the fractional change in length, or this quantity, the fractional change in length is also called the strain, is called the gauge factor. And the gauge factor is basically one value that tells you how a strain gauge behaves, right? So if I give you a gauge factor for a strain gauge, then you can very easily find out what the change in resistance would be for a particular strain. And of course, from this equation, you can easily see that it turns out to be this. And what we want is, we want this resistive effect to disappear, and we want this gauge factor to be a constant, and that would be great. You can, what I've done here is I've just listed a few materials that I used for strain gauges, and here are gauge factors. Now, all these materials above silicon, not including silicon, all these materials are metallic metals or metal alloys. And you can see that the gauge factor of these are quite low, right, compared to these the bottom four things. The silicon and germanium are semiconductors, they are not metals, and their gauge factors are much higher than the gauge factors of these. However, so you might think that, oh, we may want to use these semiconductors instead of these metals because the gauge factor is more, which means that for a particular strain, you will get a larger change in resistance, and so the sensitivity of our sensors is going to be greater. But the problem is that along with this high gauge factors, we also get a very high temperature coefficient of resistivity. Okay, so as I said before, that the gauge factor not only depends on the dimensional effect, the change in resistance not only depends on the dimensional effect, but also the piezoresistive effect. And the piezoresistive effect depends on temperature. So the resistivity of a material depends on temperature, as you can imagine. And for semiconductor strain gauges, the temperature coefficient of resistivity is very high. Now, what is the problem with that? So, our sensor, the strain gauge, is not only sensitive then to strain, but it's also sensitive to temperature. And that would cause all kinds of problems when you're trying to make measurements. So, commonly for strain gauges, we tend to use metallic strain gauges, which have a low temperature coefficient of resistivity.